Alright, so we're back with the paper. Essentially, if I have any, I guess, gene, it's going to have this type of distribution. It's called a bell curve, where we have an average and then we have outliers. So height is a very good example, average height and then outliers. And as we go out, we're losing the population. So this is like 99% of the population here, and then more extreme, more extreme. What can end up happening is that changes in environments can actually change the allele frequency. So over time, human height has actually increased from like, I don't know, like 5 foot to probably 5'10" or something. Just throwing out the numbers out there, but the main point is that we've actually seen a shift in allele frequency. Now imagine that this extreme super resistant bacteria is put in an environment of penicillin and over time becomes resistant. Well, the whole shift would shift towards that extreme bacteria. So this is a dynamic curve essentially. Now we're going to talk about the Hardy-Weinberg equation and obviously supplement with Luca's notes, because this is not everything of the week, but this is like the most important thing. The Hardy-Weinberg equation will almost 100% come up on the exam, but it's also really good to know because it explains a lot of things. So I notice here that changes in frequency can essentially shift our allele frequency, and that's what the Hardy-Weinberg equation is going into. So remember we had our square, right? We had our big T, small t, big T, small t, just an example of allele frequency. So you'll notice something right here, which is that these small t's kind of, if we assign them the letter of Q, they essentially are Q squared because it's two T alleles multiplying with each other. And then let's say this is our P. Well, this is like P squared. So this is two big dominant alleles multiplying each other. And then a mix here is just 2PQ. So whenever you cross the F1 generation, or basically one of each allele, you end up getting this ratio of P squared plus 2PQ plus Q squared. That's how we got the equation, but that's not important to know. The main thing is that we have this equation which can describe certain allele frequencies, and it has some conditions. So the large breeding, it must be a large breeding population, random mating, no mutations in allele, no migration, no selection. The reason why we have this is because technically it's not going to follow this ratio if there is a certain selection. So let's say our individual environment only favors short individuals. As such, you're not going to get this bell curve to simplify the math, and you're not going to get this frequency because you're selecting for a certain thing. So this is also examinable. You should know all of these conditions. In terms of the equation, we're getting P squared plus 2P squared, plus 2PQ plus Q squared. And essentially, this is just the frequency of one allele. So P is the frequency of one allele, Q is the frequency of one allele. We have another equation, which is P plus Q equals 1. This is kind of common sense, which is that if I have one allele, the variant of that other allele as a proportion must equal 1. So it's kind of like a math thing. If you have to memorize it, memorize it. Now I want to do some questions because these equations look quite simple, but the questions can get quite complicated. So if we have an allele, right, and let's say this allele is a big D allele or a big T or whatever symbol you want, really. So its frequency is going to be 0.24. Right away, we can deduce that the little d is going to be 0.76. And essentially, if we're asked to calculate what's the heterozygote allele frequency, we just plug it right into the equation. So 2PQ, 2 times 0.24 times 0.76, that gives us 36.5%. It gives us a decimal, but I've just converted it into percentage. Now, what happens if we're given a double B or we're given a TT? And we're basically told that this is represented as 0.36%, then what's going to be the chance of getting a little t? So we're basically asking, well, we know this ratio here, what's the chance of getting the little t's here? And notice how it's not going to be like 75% because you have a big T here and you would have a big T here. So you have to account for those. And the way we do that is, remember, P itself is our single big T. It's not TT. P is just a single big T, right? Two P's together is what makes our TT. One P and one Q is what makes our heterozygotes, and two Q's is what makes our small t's there. Therefore, here we're given two of our big b's here, or our big t's really, doesn't matter. Therefore, we must do the square root, because the opposite of an exponent is a square root, and only by doing the opposite can we actually know what our p is going to, what our b is going to be, our single b or our p essentially. So the square root of that is 0.6, and therefore our single Beal's allele frequency is going to be 0.6, and as an extension, our q, whatever we choose that to, whatever symbol we want for that, so let's say little b, that by extension would be 0.4. Why? Because p plus q equals 1. That is actually one of the simpler questions. Now, if we have cc, c lowercase c, lowercase c, lowercase c, and our allele frequencies are 0.5, 0.25, and 0.25, and essentially I'm just trying to write here that the c is essentially our p, right? The single big C is our p. Two big C's is what's making our p squared. Here I'm telling you that the frequency of this is 0.5. Our not our 2pq, but the frequency of the heterozygotes in the population is 0.25. Sorry, this one's 0.5, and this is 0.25. What would be the allele frequency of just one big C? And this is actually how you would be collecting data, because remember, you'd be seeing the phenotypical change, not necessarily the genotypes. So how would you figure out what's the allele frequency of the big C there? We can actually use this quite a smart method. You'll notice here that we have two big C's here, and one big C here, one small c here, and two small c's here. So if we know that the allele frequency, if we're trying to figure out find the big C allele frequency, and we know that 0.5 represents two of them, and 0.25 is, let's say, a half of the big C, or essentially if we divide the 0.25 by 2, we get the big C allele frequencies in this heterozygote, if that makes sense, right? Because 0.25 is the allele frequency of the big C and the small c. So if we divide it by 2, we only get the allele frequency of the big C there. As such, 0.5 plus 1/2 of our big C, small c, or 0.5 divided by 2, is going to give us 0.625. And that essentially is our allele frequency of our big C. Go over this a couple times if it doesn't make sense. It took me like 3-4 times to really get my head around it. So now we know that our P essentially, or our big C, is going to be 0.625. And right away from here, I can calculate the Q just from P plus Q equals 1. And then I can also calculate my P squared, my 2PQ, and my Q squared, because once I have my P and my Q, I can basically calculate anything. So that's how you deal with that question.